All right, guys, this video is going to cover your first real set of notes for the class. This first unit is going to be all about biochemistry. And so we're going to start by just kind of doing a basic chemistry review. And we're going to go through just the chemistry portion of this notes, and then we'll do the water tomorrow. And so you might be wondering, why are we covering chemistry when this is biology? And really it's because life depends on chemistry. We are made up of chemical compounds. Inside of our cells, we have metabolism taking place, which is all of those chemical reactions. And so before we get into macromolecules that make up our cells and bodies, and before we get into metabolism and chemical reactions, it's important that you guys have a basic background on just some chemical concepts. And so just a very brief review. A lot of this stuff is stuff that you guys started going over as early as middle school. And so some of it's not going to be new to you. You just kind of have to refresh your brain a little bit. There will be maybe some new things that are new to you, but for the most part, this is just going to be a review of old things. So hopefully you know that matter is anything that has mass and takes up space. That's pretty much everything, your solids, your liquids, your gases. Matter does not include things like energy and forces, like sound or light or gravity. But everything else, anything that has mass, is going to be made up of atoms, and that's going to be your basic unit. The atom makes up everything. Now, as we move through this class, we're going to get into the different levels of organization, and we know that cells make up living things, but even the cells that make up living things are going to be made up of atoms. And an atom consists of 3 subatomic particles. We have protons, which are positive, and neutrons, which are neutral. Don't get in the habit of saying protons positive, neutrons negative. Okay, don't make that mistake. So it's P in positive and N in neutral. So protons are positive, neutrons are neutral. And these two together are going to be found in the nucleus of the atom. Sorry about the highlighting. I'm doing this on a laptop without a mouse, and so it's a little bit squiggly. But both of your protons and neutrons, they're going to be found in the nucleus of the atom. And as you can see in the diagram over here, the nucleus is also going to be what gives the atom its mass. Okay, the mass of the atom is going to be found right here with those 2 particles. And so with the protons being positive and the neutrons being neutral, that nucleus is going to have an overall charge of positive. Now, around the nucleus in the electron cloud, you're going to have the electrons, which are your negatively charged particles, and they are essentially going to give you the volume of the atom. They're outside in these different energy levels. They're moving around, and they're giving that volume. It's called a cloud because they're in motion, and so they're constantly moving out there. And so those are going to be your 3 subatomic particles. Now, some important vocabulary to know, and if you've ever spent time with the periodic table, you should be somewhat familiar with these things. But the atomic number is the number of protons, and that's what determines the element. Remember, like things like carbon. Carbon is always going to have 6 protons. That's its atomic number. Oxygen is always going to be 8. Hydrogen is always going to be 1. Sodium is always going to be 11. And so the protons determine what the element is, and if the protons change, it is no longer the same element. Then you have your mass number and your atomic mass. Now, on the periodic table, what you're going to find is the atomic mass, and that's going to be the decimal number because it's an average. So like carbon, the atomic mass is like 12.001 or 12.011, something along those lines. And you find those decimals because not all atoms of that element have the exact same mass. And so whereas the atomic mass is an average, the mass number is specifically referring to the mass of one atom. Okay? And you can see that it's the protons and the neutrons that are giving that mass. So when we get into isotopes here shortly, we identify them by their mass number, which is the number of protons and neutrons that one particular atom has. And since isotopes exist, then on the periodic table, what we get is the atomic mass, and that's where that average comes from. All right, so by definition, atoms are neutral. And so anytime something is referred to as an atom, carbon atom, oxygen atom, helium atom, anytime it's referred to as an atom, we know that the protons are going to be equal to the electrons. So the protons are positive. They determine what that element is. The electrons are negative, they're out there in that cloud. And so in order for the atoms to be neutral, then the protons and the electrons would have to be the same. Now, the thing is atoms may not be kind of quote unquote happy in that state. And so sometimes what will happen is in forming bonds, atoms will either lose electrons or they'll gain electrons. And at that point, we no longer call them an atom, we now call them an ion. And so an ion, by definition, is a charged particle, okay? Now, if an atom were to lose an electron, they now have more protons than electrons, and that gives them an overall positive charge, and we call those cations. And then if they were to gain electrons, then what's going to happen is they're now going to have more negatives than positives, and we call those anions. Now, this is totally dumb, but one study tip that I recommend is anytime something makes you think of something else, you can kind of use that to help you remember some terms that maybe you're not familiar with. And so this is silly and it may not help you, but one of the ways I've always remembered cation versus anion is cation has the word cat in it, and a lot of times people like cats. You know, kittens are cute and they do funny things in videos and stuff like that. And so a lot of times cats have a positive connotation. So a cation is a positive ion. And then to me, the word anion looks like onion. And there's a lot of people that have negative feelings about onions. You know, they can maybe don't taste good, or maybe they make you cry, whatever it may be. And so I just try to remember that the cats are positive and then the onions are negative, and so that kind of helps me distinguish between the two. It's silly, I know, but maybe that'll help you if you didn't already know that. All right, so the protons for a particular atom, for a particular element, never change. If the electrons vary, like we just saw, if electrons are lost or gained, what we get are ions. Now, if the neutrons vary, that is when we get an isotope. So an isotope, by definition, are atoms of the same element that have different numbers of neutrons. Now remember, the protons are going to stay the same. Carbon will always have 6 protons, oxygen will always have 8 protons, sodium will always have 11 protons. But the neutrons can vary, and the only thing that will affect on that atom is the mass of the atom. So remember that the neutrons have no charge, and so they're not going to affect the charge. They won't lead to ions in any way. They don't really affect the behavior of the atom, because that's going to be the electrons, and we'll talk about that here in a minute. But what the neutrons will change is the mass, and that's why we use a mass number. The mass number is going to identify a particular atom of that element rather than just the average like we see on the periodic table. And so anytime you have isotopes, a lot of times they're represented in this way. So here you have the chemical symbol for carbon. The atomic number is going to be 6. Remember, that never changes. And then there you have the mass number for those carbon atoms. You could have carbon 12, you could have carbon 14, you could have carbon 13. Sometimes you'll see them written with the actual name of the element, like carbon will be written out and it'll say -12 or carbon -14. And so both of those are just ways to represent isotopes. And so the chemical properties are going to be the same. The only thing that will be different is the mass, and that's why we use the mass number to represent them. And so this is also how we can calculate neutrons in an atom. We know the protons because of the atomic number, and so to get neutrons, we just simply have to subtract the 2. Now, some isotopes are not stable, and essentially the nucleus, those particles are not kind of really in a stable state. And so what they will do is, in order to get to a more stable state, they will spontaneously give off particles, and we call those particles radiation. And so any isotope that is unstable and gives off particles, alpha, beta, gamma, you may have learned about those in chemistry. When they give off those radiation particles, what we can do is we can actually use those for different purposes. Now, radiation is bad, and exposure to radiation could be harmful to us, especially when we get up into those like gamma rays and things that are really, really high energy. Radiation is bad. We don't want to be exposed to radiation, but we can target and use them for some beneficial purposes. So we can use them like in dating of fossils and rocks. You may have heard of carbon dating before. And that just involves using the half-life of different elements. And as they decay, they become different elements. And so they can look at ratios. There's a mathematical thing for that. But they can kind of determine the age of rocks and fossils. We can also use them kind of to kill bacteria, kind of like as a, the word's not coming to me, almost like a sanitizer of sorts. We can expose bacteria or utensils to some of this radiation, and it can kill those bacteria. And we can also use it to treat cancer. Now, it's highly targeted. Obviously, radiation is not good for us, and this is why there are lots of negative side effects to radiation treatments. But by targeting those cancer cells, hopefully we can disrupt them with that radiation. And then we can also use the radioisotopes for tracers. And so for things like PET scans, what they can do is they can give you a radioactive form of an element, and your body will use that just like it uses the non-radioactive form. And they can physically, with instruments, trace that radiation through your body. So they can look at where certain elements are collecting, they can look at pathways, and so they can be really helpful for like medical diagnoses and things of that nature. All right, and so that takes us to elements. So an element is just a pure substance. This is what you'll find on the periodic table. And as we move forward in our biochemistry unit, we're going to talk about macromolecules. And these macromolecules or biomolecules, they are big molecules that are essentially organic compounds. And so of all the elements that make up living things, there's a whole bunch of them. But of all the elements, about 25 are essential to life, but 4 of them, once again, sorry about the highlighting, 4 of them are going to be making up the majority of living cells. So we have 96% of living organisms is going to be made up of carbon, oxygen, hydrogen, and nitrogen. If you don't know what those chemical symbols are, you might want to jot that down. Once again, that's carbon, oxygen, hydrogen, and nitrogen. And so the good bulk of our bodies are going to be those 4 elements. The reason being macromolecules and water. So obviously H2O is a big component of our body. So there you see those 2 elements. And then all of your macromolecules have carbon backbones attached to hydrogen. And then you'll find nitrogen in things like our proteins and our nucleic acids. And so that's why those are going to be the top 4. Anything else is what we consider a trace element, and there's definitely other elements that we cannot live without. They may be electrolytes, or they're going to be components in our metabolic activities, things like sodium, iron, calcium, these down here, copper, iron. So there's a lot of different elements that make up. You do not have to know these numbers. This is just a kind of an FYI, just to show you some of the elements and their percentages in the human body. But just kind of know that there are others that are required. But those 4, carbon, oxygen, hydrogen, and nitrogen, make up the bulk of your living cells. All right, now we're going to get into molecules and compounds. And so atoms, we talked about earlier, make up everything. And atoms are going to bond to form molecules and compounds. Now, for years and years and years, I taught that all compounds are molecules, but not all molecules are compounds. And technically that's not right, because when you get into ionic compounds, there's some different vocabulary. So what you need to know about these 2 are just kind of the main differences. So a molecule is any 2 or more atoms bonded together. So here you can see like hydrogen gas, oxygen gas, water. You can have a molecule of water, a molecule of oxygen gas. But a compound specifically has 2 or more elements. And so what you're going to be looking for to identify if it's a compound is, does it have at least 2 capital letters in that chemical formula? So water is also a compound. You can have a molecule of water, but that's also going to be a compound. Whereas these gases here would be molecules only. Notice they do not have 2 different elements that are in that chemical formula. So down here we have sodium chloride or salt. We have glucose. These are both important formulas to know, especially good old glucose, the sugars that we use for energy. And so what atoms are going to do is they're going to bond to form these molecules and compounds. And it's all about the electrons. So earlier we mentioned that the protons and the neutrons give the atom its mass. The electrons are going to determine the behavior of the atoms, especially what we call the valence electrons, the ones that are on the outermost shell. And so remember that your protons and neutrons are here in the nucleus, and that nucleus has an overall positive charge. And that's what keeps those negative electrons from just flying off into space, is that attraction. But the further away you go from that nucleus, the more energy those electrons are going to have, because they're not going to be as tightly held. They're going to be more energetic, they're going to be more unstable. And so it's going to be these electrons that are furthest away from the nucleus that are going to be responsible for the behavior of our atoms. And we call those valence electrons. And I'm sure back in chemistry you did the dot diagrams, and you did the different orbitals, the 2p and all that kind of stuff. Honestly, I don't remember all of that. But that just has to do with those different energy levels. And so for most atoms, they want to have 8 valence electrons in order to kind of be stable and what I say is happy. I know that's probably not proper terminology, but in order for atoms to be happy, they want to have a full outer shell. Now remember, for hydrogen and helium, they only need 2 because that first orbital holds 2 electrons, and after that it's 8. And so what will happen is, if atoms do not have a full outer shell, they're going to interact with other atoms. They're going to form bonds in order to fulfill those valence numbers, which, like I said, for most of them is going to be 8. And so this is what's going to lead to bonding. And we're going to talk about 2 main types of what we call intramolecular bonds, and that means within the bond. So this is how we're going to make molecules and compounds, is by these bonding between atoms to form these molecules and compounds. And so one major bond type that you need to know is covalent. And I'm going to give you a key word for each one. And the key word for covalent is shared. In covalent bonds, electrons are shared. And so in this case, this is going to be a very, very strong bond. We represent these with solid lines, and that indicates their strength. They're going to be much harder to break. And these covalent bonds are going to be what you find in your big macromolecules. And so essentially what will happen is 2 atoms will hang out close enough, and they will share one pair or multiple pairs of electrons. And that way they both get that fulfillment of a full outer shell. So one of the most common examples of a covalent bond is what you will find within the water molecule. So hydrogen needs 1 more valence electron to be happy. Oxygen needs 2 more valence electrons to be happy, and that's why that oxygen is going to bind with 2 hydrogens. And this is going to be a very strong bond between them. And we'll look more at that here in a moment. But once again, the key word to covalent is shared. Covalent equals sharing. And if we break that word down, a lot of times co means both or to share, like co-captains are going to share the duties of whatever they're captaining. And so valent refers to valence electrons. So literally we're talking about sharing valent electrons here. Now the thing is when it comes to covalent bonds, the sharing may not always be equal. And that's because of something called electronegativity. Some atoms like electrons more than others. And this is a silly example, but I always give an example of me and Dove dark chocolates. So I really, really like Dove dark chocolates. I like any kind, almond, caramel, whatever. And I like to consider myself a pretty nice person. And if I had a bowl of dark chocolate Dove sitting on my desk and you were to walk into my office, I would probably offer you one because I'm a nice person like that. However, I am not going to give you half of my bowl because I like the Dove chocolates more than you do. And so our atoms are the same way sometimes. Sometimes there's going to be an equal sharing, and sometimes there will be an unequal sharing. It really just depends on the electronegativity of the atoms that are in that compound. If you have a certain atom, such as oxygen, oxygen has a high electronegativity, nitrogen has a high electronegativity. If they like the electrons more than the atoms they are bonded with, what can happen is the electrons may not be shared equally. And so what happens is polar compounds will form. And so what we get in a covalent bond is either a nonpolar covalent bond, and this is when the sharing is equal, or we get a polar covalent bond, and this is when the sharing is unequal. If it's equal, there's going to be no poles or charged regions of the molecule, and typically these are going to be symmetrical, like methane, CH4, that is going to be a nonpolar molecule. A lot of your carbon compounds, like your fats, your fatty acids, a lot of those are going to be nonpolar. Now, if you do have an atom that has a higher electronegativity, what's going to happen is that atom is going to hold the electrons closer to it. It's still going to be a sharing. Okay, anytime it's covalent, there's a sharing of electrons. But if it's an unequal sharing, what's going to happen is the molecule will get these partial charges. So here's a nonpolar molecule. Notice there's nothing really written around the outside. It's going to be a symmetrical type of structure. But water is a prime example. Now what happens is the oxygen here becomes the electron hog, and it holds the electrons closer to this end of the molecule. And so what happens is that oxygen becomes kind of negative. Now this isn't a full-on ionic charge. It's just kind of a weak partial charge. And when that oxygen becomes kind of negative, these hydrogens become kind of positive. And that's what we call our poles. Okay, that's why we call it a polar molecule. So our next type of bond is going to be an ionic bond. So the key word to covalent was a sharing. Whether it's equal or unequal, it doesn't matter. Okay, covalent equals a sharing of electrons. But sometimes that force of electron attraction is so strong that literally electrons will be lost or gained. And that's when we move from a covalent bond to an ionic bond. And so the key word for ionic is that electrons are transferred. We literally are going to have a loss and a gain of electrons, creating ions. Okay, so when something is so electronegative that it literally strips the electron from another atom, they are no longer atoms anymore. They are now ions. And so, as you probably know, opposites attract. And so what will happen is when one loses an electron, it becomes positive. And when another atom gains an electron, it now becomes a negative ion. And now those positives and negatives will attract to each other. And that's what we call an ionic compound. Okay, these also form what we call salts. Sodium chloride is a prime example. So sodium over here has one measly valence electron, so it can either lose one or gain 7. And so sodium is more than happy to give away this electron. Chlorine over here has 7 valence electrons, so it only needs one more to have a full outer shell. It can either gain 1 or lose 7, so once again, it's just looking for an electron to take. And so when sodium transfers that electron to chlorine, sodium becomes a cation, chlorine becomes an anion, and now we have opposites attract, and that's what forms an ionic bond. Now, ionic bonds are pretty strong until you put them in water. They do break up easily in water, and so they are not nearly as strong as a covalent bond. And then we have hydrogen bonds. So once again, the key word to covalent was a sharing. The key word to ionic is a transfer of electrons. And for hydrogen bonds, the key word that I want you to remember is weak. Hydrogen bonds are very, very weak. And earlier we talked about intramolecular bonds. So covalent and ionic were intramolecular. That means within the molecule. Hydrogen bonds are going to be intermolecular, which means between the molecules. So typically what's going to happen is a hydrogen bond is going to form between polar compounds. Okay, so kind of go back to that polar versus nonpolar. Remember that polar molecules are made when electrons are not shared equally. And so what happens is you get that bond that creates kind of partially negative regions and partially positive regions. And so what a hydrogen bond is it's going to be a weak attraction between those weak charges. Okay, once again, hydrogen bonds are going to form between molecules. So here you have water molecules. This is what holds them together. And when we get to our water lesson tomorrow, this is what we're going to talk about again. But the oxygen is kind of negative. The hydrogen regions are kind of positive. And so a hydrogen bond is a weak attraction between those partial charges. Notice the hydrogen bonds are represented by dots, and that signifies that weakness. Now, hydrogen bonds are super significant in biology. Just 2 examples of where you're going to see them. There's actually more. But hydrogen bonds hold water molecules together, and it's going to be responsible for many of the properties that water has. Hydrogen bonds also are found between the 2 strands of DNA. And that's going to be really important because in order to copy our DNA, in order to turn it into RNA, in order to replicate it, we have to break these bonds. And so if they were really, really strong, that would be problematic. And so hydrogen bonds are very significant in biology. All right, so just a quick recap on bonds, okay? In order for atoms to be happy, they want a full outer shell. And so valence electrons are going to be responsible for bonding. Now, if the electrons are shared, they form what's called a covalent bond. If they're shared equally, we get nonpolar compounds. If they're shared unequally, we get polar compounds. Ionic bonds are a bond that is formed because electrons are transferred from one atom to another, creating ions. And then hydrogen bonds are weak bonds between polar molecules. Okay. All right. So now we're going to move on to a couple more topics before we wrap up chemistry. One is chemical reactions. One of our lessons in biochem is metabolism, and so we need to understand just some basics about chemical reactions. Pretty much all we're doing is making or breaking bonds. That's all a chemical reaction is. Remember that matter is not created or destroyed, that law of conservation of mass. All we're doing is just kind of rearranging our atoms into new compounds, or we're breaking them into smaller compounds or elements or whatever it may be. And so on a chemical reaction, the basic setup is you always have your reactants on the left. It's whatever you're starting with. You always have your products on the right. And that chemical reaction will essentially proceed until you get to chemical equilibrium. And that's where your concentrations are going to be stabilized, and there's no net movement one direction or the other. We're also going to take a look at organic chemistry, and organic chemistry is what we're kind of studying when we do our macromolecules. Organic chemistry is the study of carbon compounds, especially carbon attached to hydrogens. Typically carbon compounds, or these organic compounds, these are going to be your life compounds, the ones that make up living things. Carbon dioxide is not necessarily considered an organic compound. It really just depends on what resource you're looking at. But normally it's carbon bonded to hydrogens. And so carbon has 4, didn't mean to do that. Carbon has 4 valence electrons, and so it typically forms 4 bonds. A lot of times that's going to be with hydrogens. It forms what's called hydrocarbons. And these are going to be the backbone for a lot of your big biomolecules or macromolecules that we're going to be covering in a couple of lessons. So the carbon skeletons can vary, and something that you need to understand that's kind of a backbone concept of biology, or really anything, is that structure determines function. And so the structure of these carbon compounds is going to determine the functions that they have. And so the carbon skeletons can vary. They may have single or double bonds. They may be branched. They may be in a ring. Some are huge. Some are smaller. And then sometimes you'll come across isomers. And isomers are chemicals that have the same compound, like the same compound formula, but they are structured differently. So one example is like glucose and fructose. Now, fructose kind of gets a bad rap. A lot of times you hear about high fructose corn syrup, and glucose is a sugar that's in our blood. It's the main one that we use for energy. But they both have the formula C6H12O6. However, it's the structure, it's how those carbons, hydrogens, and oxygens are bonded together that makes the difference between glucose and fructose. If those bonds are in slightly different positions, then it's no longer going to be the exact same compound. So same chemical formula, but different structures and therefore different properties. And sometimes this can be kind of dangerous. There have been medications where one form or one isomer is not harmful, but if it gets converted to another form, sometimes they have some negative side effects. And so we do have to be careful because the body will use them differently. And so the isomers are something that they have to keep in mind, especially like in pharmaceuticals. All right, and then functional groups. Now on your notes, you're looking at a chart. I'm going to show you a picture here in a second. Actually, it looks something like that, okay? Now functional groups, think of them kind of like as add-ons to compounds. So a lot of your macromolecules or a lot of your organic compounds, they have this carbon skeleton, carbons attached to hydrogens. But imagine that you kind of just tacked on another little piece to those backbones. And sometimes those little attachments are going to give that molecule certain properties, okay? So a functional group is just kind of like an arrangement of atoms, like a little compound or a little molecule that's going to be attached to those carbon skeletons. And when that happens, it's going to give it certain properties. Now, when you take your quiz is actually going to be over chemistry and water and macromolecules all in one, and I'll be giving you more details on that later. You will see at least one question. Okay, you have a lot of material on your quiz, but you will see at least one question from this chart. Okay, and you have it there on your paper, and so you don't have to memorize the whole chart. But the kind of questions that you could see are about the functional group. So this column here, okay, all of these functional group names, all right. What I need you to know for quiz purposes and for test purposes is the group name and essentially the significance of what that's going to do to the compound. So what are going to be the properties that this functional group will give to that particular compound? Okay, so for example here, we have hydroxyl group. It is an OH, okay? You don't have to necessarily know the chemical formulas. It may not hurt to look at them, but you're not going to be asked what is the chemical formula for a hydroxyl group. And so your hydroxyl group, it's going to give it polar properties. Now, why is that significant? Well, if something is polar, it will dissolve in water, okay? If something is polar, it can form hydrogen bonds. And so by having hydroxyl groups, things like sugars and amino acids can have them. A lot of times that means that they will dissolve in water. So for quiz purposes, what you would need to know is that a hydroxyl group gives it polar properties. Okay, really that's all this is saying over here. The carbonyl group, once again, polar properties. Carboxyl group. Now this one's kind of important because I want you to take a look at these two together. We have a carboxyl group and we have an amino group. Now, sometimes these are called carboxylic acids, like we see here. But notice that the carboxyl groups give it polar properties, but it also makes it acidic. Okay? And then the amino group over here is going to make it basic. And so these two groups are actually on what's called an amino acid. So one end of the amino acid is going to be basic, and one end of the amino acid is going to be acidic. And so that's going to be some unique properties. You have sulfhydryl. These are going to be in proteins, and they can be important in forming some bonds. And then phosphate groups, we're going to see those pop up multiple times. But phosphate groups can transfer energy. They can be polar and acidic. And so all you have to know, once again, for quiz purposes, is just kind of be familiar with the name and the significance and what it does in those compounds, okay? So literally probably like one question on your quiz will come from your functional groups. And as we move forward, like in macromolecules, you'll see some of these pop back up, and that's why I just kind of want you to be familiar with them. And that's where we're going to stop in this video. You should be getting your study guide today. I talked about those on Friday. And so I just want to remind you that in your study guide, you do have some practice. There's a crossword puzzle, there's some practice questions, and so I would encourage you to take a look at that. We're not ready to look at the essay just yet, but hopefully when you have some time in class, when the lesson doesn't take the whole class period, maybe you can use that time to check out your study guide. All right, that's going to be all for today. Y'all have a great one.